Hi there and welcome from Ventura, California to today's webinar sponsored by Sensonor, Inside GNSS, and Inside Unmanned Systems, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we will be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address the topic at hand. Inertial navigation joins forces with GNSS all across the spectrum of PNT requirements from low to high. We're about to take a close-up look at one of the highest requirements, a blast off into space, and we invite you along for the ride. And in the process, you'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Expert panel session with all three of our panel members. Now, we've invited you along with over 525 professionals across 50 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher Inside GNSS, Inside Unmanned Systems, would like to take just a moment to welcome you and introduce our sponsor and main moderator for today. Richard?
Thanks so much, Lori. On behalf of Inside GNSS, Inside Unmanned Systems, and today's sponsor, Sensonor, I extend a warm welcome to our audience from around the world for today's web seminar. We value your participation, and we're delighted that you're with us today. I'd like to introduce Hans Richard Peterson of Sensonor. Mr. Peterson has more than 20 years of international business and technical experience and is in charge of product development and global marketing at Sensonor. Prior to joining Sensonor, he worked for the Norwegian Trade and Technology Office in Silicon Valley. Hans Richard, welcome.
Yeah, Richard, thank you for that introduction. At Sensonor, we have worked with Inside GNSS now for more than 10 years, and we have also enjoyed their focused engagement in the position, navigation, GNSS community. At Sensonor, we have only been active in this technical grade gyro segment for about a decade. We have seen our IMUs and gyros utilized in almost every application in every industry segment. Many applications we did not even know existed when we designed the IMU and the gyros. For the last 8 years, I have been very fascinated by the range of new space and old space companies that have chosen to fly over parts in space, even not designed for space originally. NASA was the first one to fly over parts on several missions, and we have flown parts continuously for at least 8 years with them. We have also had installations at the International Space Station for the last 3 years. Today, we think that more than 300 units fly in commercial new space LEO satellites. We also see installations in several launch providers coming now, and started to see that the standard IMU is flown successfully to the moon and is today also planned for several new lunar missions. Space is by no means the primary business of Sensonor. However, we see the extensive use in this segment as an evidence of reliability and trust. We think also that this is a great reference to have. Please note that the components that we ship to the space segment are standard parts with no difference compared to what is shipped to other markets or applications. So, with these words, I really look forward to this webinar today that will address the technology, space applications, and also reliability by design process. So, with that, back to you, Richard.
Thank you, Hans. I appreciate those comments. We've done more than a couple of webinars on GNSS inertial integration, but never have we had any discussion regarding the use of such sensors in space. So the audience is in for a real treat today. So without further ado, I'd like to introduce Alan Cameron, who will be our moderator. And Mr. Cameron's the editor-in-chief of Inside GNSS magazine and the PNT editor for Inside Unmanned Systems magazine. Alan's covered the GNSS, PNT, and autonomous industries and research communities as a writer and an editor since 2000, focusing on technical issues around continuous, reliable positioning and navigation. Alan, the floor is yours, sir.
Thank you very much, Richard, and welcome again to our audience from around the world. We're in for a very exciting webinar. I don't mind telling you that as I watch this webinar come together, and we do prepare it rather intensely, I have learned something new each time we go through the material. Of course, the first time I learned the most, but each time I saw it again, I picked up some more, and there's just a real depth and richness to this. Perhaps that says something more about the shallowness of my learning curve, but at any rate, it's an exciting webinar coming up. Before we get into the webinar itself, Lori, let's learn a little bit about our audience with the first of our poll questions.
Absolutely. Coming up on your screen is that first poll question, and we'd love to hear from you. Which of the following best describes your application of inertial technology, or the one that you are most interested in applying? Choices there are automobile, machine control and precision ag, UAV, tactical missile, space satellite. It looks like we've got 15% saying automobile, 15% machine control and precision ag, 35% UAV, 6% tactile missile, and 29% coming in with space and satellite. Alan, any thoughts here?
Well, it's a little bit surprising. Of course, we do have a space and satellite use case as part of this webinar. That's not the only thing. I want to hasten to tell the audience that we're going to be addressing, but it is kind of the demo that will roll out in the final third or the third quarter of the webinar. But space and satellite is a relatively small segment, and that we have such great representation from it is wonderful. Of course, UAVs are the going thing nowadays with a lot of inertial applications, but I'm heartened to see that automobile and machine control and precision ag are also well represented. Of course, tactical missiles, that may be the smallest segment, but we have some there as well. And there'll be a few notes sounded in that respect. All right. We've gotten to know our audience a little bit better. Let's get to know our first presenter. Ralph Hopkins is a distinguished member of the technical staff and group leader in the Positioning, Navigation, and Timing Division at Draper. He is responsible for the design and development of inertial instruments and sensors. Ralph has served as Technical Director of Advanced Inertial Instrument Development Programs, including strategic, navigation, and tactical grade gyroscopes and accelerometers. He is an invited speaker for short course tutorials on inertial instruments and inertial technology, and has presented internationally for the NATO Science Technology Organization-sponsored lecture series and symposia on navigation technology. He holds a bachelor's and master's in mechanical engineering from Rensselaer Polytechnic Institute, a master's in engineering mechanics from Columbia University, and a master's in engineering management from the Gordon Institute of Tufts University. Ralph, I look forward to your presentation.
Thank you, Alan. Good afternoon, everybody. So our discussion today will start with an overview of the current inertial sensor landscape, namely what types of gyros and accelerometers are employed in different applications and performance grades. Then we'll get into small form factor inertial sensors, specifically MEMS devices, and we'll touch on a couple of emerging technology trends, specifically those that are being explored, which may have potential in improving the performance of miniature gyroscopes. And then we'll close with some thoughts on inertial navigation augmentation and where sensor development is headed from here. So this chart is an attempt to capture the performance and application space of different gyroscope technologies. And we have the two key inertial sensor performance parameters plotted on the two axes. On the x-axis, we have bias stability, and on the y-axis, we have scale factor stability. So near the origin here, we're in a region of very high strategic grade performance. And as we move out diagonally, we enter into navigation grade and coarser tactical grade and consumer grade performance. And this chart illustrates what I like to call the small gyro problem, in that miniature MEMS technology which takes up this space here, hits a performance wall around the 1 degree an hour bias stability range. Currently, your higher performing gyros are all larger scale devices such as optical and good old-fashioned spinning wheel gyros. And this is in contrast to the corresponding situation with accelerometers. Here we have the same plot with bias stability on the x-axis, scale factor stability on the y-axis, and notice that the miniature MEMS accelerometer space spans a very broad region of the performance range and penetrates quite deeply into the higher performance application space. This next chart is an example of just some of the miniature MEMS gyros that have been developed over the past 20 years or so. All of these are Coriolis vibratory gyroscopes in that they employ a vibrating transducer element, such as a ring or a tuning fork, that's driven at resonance. An applied angular rotation rate introduces a Coriolis force loading on the resonating element, which by structural design couples into an orthogonal resonant mode whose response is an indication of the applied rate. Likewise, some examples of MEMS accelerometers are shown in this chart. Some of these use tension and compression in vibrating beam elements to indicate acceleration via shifts in resonant frequency. Others simply use the measured deflection of a flexure-supported mass to indicate acceleration. So if you're in the business of making miniature MEMS gyros and accelerometers, well, you're going to make a MEMS-based IMU. And this has been the single biggest development in PNNT in the last 20 years, namely the ability to add a guidance, navigation, and control function to vehicles such as artillery shells, UAVs, and so forth, where it was previously impractical to do so because of size, weight, and power considerations. These two examples up here, the United Technologies and the Honeywell IMUs, are examples of gun-hard products capable of surviving firing launches of up to 20,000 Gs. Some of these other MEMS IMUs are integrated with GPS receivers, which furnish then a GPS inertial integrated solution with GPS limited position accuracy. This next chart shows some initiatives in miniature gyro development that are intended to squeeze better performance out of a miniature transducer element. These are all Coriolis vibratory gyros of the ring resonator type that are somewhat inspired by the hemispherical resonator gyro, a very high performance bulk size gyro that uses a wine glass shaped resonator. If you take one of your nice crystal wine glasses at home and flick the rim with your finger, you'll hear a nice clear tone ring out. But actually there are two vibration modes going on that lie spatially at 45 degrees to each other. And if you listen carefully, you may hear a lower frequency wobble, which is the beat frequency between those two modes. If you rotate your wine glass along the axis of its stem, you'll introduce Coriolis loading on the rim, which drives energy from one of the wine glass modes into the other, causing a precession of the net mode shape around the rim perimeter that is measured as an indication of the applied rate. So these top two designs here are silicon MEMS versions of that idea collapsed down to a 2D planar structure that you can think of as a vibrating onion slice. Improved performance is achieved via more transducer mass per unit volume engaged in the sensing rate. These lower two gyros are attempts at miniaturizing the wine glass directly and incorporate novel new microfabrication processes, namely CVD thin film diamond processing, and over here the University of California Irvine example of a microscale glass blowing process. The ability to control resonator uniformity and or trim and tune the resonator frequencies will be the key to victory in these designs. Optical gyroscopes are worth a mention here. Normally, they are not thought of as candidates for miniaturization because they derive their performance through their size. The total optical path length and the diameter of the optical path length control overall sensitivity. However, there is an optical gyro architecture that's a hybrid of the conventional ring laser gyro and the interferometric fiber optic gyro that has potential for miniaturization while maintaining higher performance. The ring laser gyro resolution is controlled by the sharpness of the optical cavity resonance, or finesse. IFOG resolution is driven by the overall path length. So by employing a fiber coil as a ring resonator, not as an interferometer path, you can combine the best attributes of both architectures, and it would permit a smaller diameter coil without sacrificing sensitivity. There are two challenges associated with this RFOG concept. One is optical fibers that allow for tighter bend radii, but there are such optical fibers in development. And then on the next slide, the need to miniaturize the associated discrete optical components found in FOGs. For example, the laser source, photodetectors, optical couplers, phase modulators, and so forth. And you're starting to see some FOG vendors employing photonic integrated circuits to miniaturize some of these off-coil components, such as this KVH example shown in the upper part of this chart. Also, the emergence of the hybrid silicon photonics technology enables fabrication of photonic components directly on low-loss waveguides. The SOI substrate's like a printed wiring board, and the CMOS layer is like the active circuit components. So with miniaturized front ends combined with tighter coil diameters, it's conceivable that you could see FOGs in a bottle cap sized form factor. So we have these terrific new miniature IMU products available to us that are driving new application areas: personal nav systems, search and rescue robots, autonomous vehicles, and so forth. And this chart shows some of these missions and mission requirements. And with the miniature IMU, we've got the size, weight, and good handle on the size, weight, and power. But look at the position accuracy required here, very high position accuracy requirement. And oh, by the way, let's do it when a GPS intermittent or denied altogether environment. These mission goals flow directly from the application space. If you're underground or in a building, GPS won't be available. Yet you need very good position accuracy because you want to know if you're on the 5th floor or the 6th floor, or am I on this side of the wall versus that side of the wall. So when GPS is denied, an inertial only solution isn't going to cut it. So additional augmentation is required, as discussed in this next chart here. And here we have some examples of position error growth shown as a function of time for 3 different system cases. And this case 1 here shows an inertial only solution using state-of-the-art gyros and accelerometers. 001 degree an hour gyro, 1 micro G accelerometer. And what this shows that with state-of-the-art inertial only, in 1 hour's time, your position error growth is going to grow to about 60 meters. Not acceptable for a personal navigator solution. And also, that type of inertial sensor performance is not currently available in a miniature form factor. The second plot over here in the upper right shows a position solution with tactical grade sensors of the performance category available in a miniature system, with intermittent GPS updates applied every 2 minutes. And here we see, a peak error of 40 meters in that type of scenario. Still really not good enough for a personal nav application. So this third system down in the corner here, this third case shows tactical grade sensors with the addition of a velocity meter to the navigation solution, something like a LiDAR, for example. And now we have a position error of only 10 meters after an hour's time which is approaching these mission goals. So this illustrates that the likely solution to these personal nav systems will be a suite of sensors such as a velocity meter, a magnetometer, an altimeter, all integrated with the GPS and inertial and an optimal nav solution to furnish the most robust solution to span GPS outages. So to conclude, MEMS inertial has proven to be a disruptive technology that has led to whole new applications in the GNSS industry. It has enabled the insertion of a GNSS function on vehicles where it was previously impractical due to size, weight, and power considerations. We briefly touched on some tech trends associated with the relentless and enduring imperative of pushing performance improvements in inertial components. Many of the emerging application areas for integrated navigation systems feature a GPS-denied scenario that will drive hardware solution architectures that incorporate a suite of augmentation sensors, where the inertial instruments serve as just another chipset in the overall design. The value prospect for developers then is in the overall integrated system performance, not in the individual components. Thanks for listening, everybody. It's been my pleasure. Back to you, Alan.
Thanks very much, Ralph. We've had a couple of questions come in already regarding the miniature gyroscopes that you discussed and also the resonating optical fiber gyro. We'll turn to those questions in our first Q&A session, which will come at the midpoint of our next presentation by Reidar Holm. Reidar Holm is a product development manager at Sensonor. He's worked at Sensonor since 1988, holding several positions within the research and development wing, starting off as test engineer for MEMS testing. He has experience in project management, MEMS design, ASIC design, low-stress package design, system design, assembly and calibration, high-volume production for automotive, MEMS pressure sensors, accelerometers, gyros, and IMUs. A man of many specializations. He has a degree in electrical engineering and electronics from the University of Manchester Institute for Science and Technology in the UK. Reidar, please proceed.
Thank you, Alan. Hello, everybody. Thank you for listening in on this webinar and giving me the opportunity to tell you a little bit about Sensonor and give you some insight into our products and some examples on how we have approached the field of tactical grade gyro modules and IMUs. I will round up with some information about ongoing activities. So, who are we? I will illustrate this by using this tree. Sensonor was founded in 1985. However, our roots go all the way back to 1965. The trunk of the tree symbolizes our solid fundament into design, production, and quality know-how based on the delivery of more than 250 million safety-critical components to the automotive applications. In 2009, Sensonor changed its focus to tactical-grade gyro modules and IMUs. These are all based on the very same MEMS gyro that was developed and used in the rollover gyro. The branches and the fruits of the tree symbolizes the large variety of applications and customers served by our standard portfolio of products, in contrast to the automotive area with limited but highly application-specific products. Sensonor has two fabs, both located in Horten, Norway. One fab for fabrication of our MEMS and one fab for assembly, calibration, and test of final products. The second facility also contains a well-equipped lab for characterizations and environmental testing. This means that Sensonor has full control of key areas such as product quality, technology, and fabrication, all at our own facility. As mentioned, Sensonor gyro modules and IMUs cover a wide range of applications within navigation and stabilization. This slide presents the main application areas into which Sensonor's products are currently used. Some of the major application areas are stabilized radars and anti-missile systems, LiDAR mapping systems, and short-term navigation. Here is an overview of Sensonor's current product offerings. From a size, weight, and power point of view, the products are very competitive, having a weight of 55 grams, a power consumption of 1.5 watts, and a size of 2.2 cubic inches. The STIM 200 series are gyro modules. The STIM 300 series are IMUs, all at tactical grade performance. The latest newcomer, the STIM 318, was introduced autumn last year. In this product, the accelerometer performance have been considerably improved compared to STIM 300. This improvement was a natural consequence of feedback from our customers using the STIM 300, pointing out that accelerometers were really the limiting factor of overall performance. 3 more products will be launched in 2020. I will come back to them later. I have pulled out some data from our production database on velocity random walk and bias instability for STIM 300 and STIM 318. The improvements are quite significant. The plots for STIM 300 represents a couple of thousand axes, and for STIM 318, a couple of hundred axes. We love nice-looking distributions. We hate freak values. Our internal production test limits are frequently reviewed to make sure we remove freaks. Key parameters like random walk and bias instability are trended over time to be able to detect unwanted changes early and correct them before they become a problem. Here is a general functional block diagram of our STIMs. All sensors are synchronously sampled. Signals are filtered and calibrated before being transmitted in data packages over RS-422. Maximum output rate is 2000 samples per second. All voltages and time references required to obtain high precision are contained within the product. An RS-422 input is also provided in order for the user to be able to reconfigure the product or request special information like serial number or detailed status information. The following functionality is covered by a 32-bit RISC-ARM microcontroller. I will now present the self-diagnostic function, which runs as a separate thread in the microcontroller, continuously monitoring the integrity of the IMU. The design of this function is a good example of our design philosophy and methods adopted from designing and delivering safety-critical components. In our philosophy, we believe in continuously providing information about the health condition of our products, and by that, give the user the best possible tools to handle the transmitted data. We started off the design of the self-diagnostic by looking at each part of the design, identifying possible failure modes and their effects. Internal voltages and timing reference come naturally high up on the list of critical items, so we wanted to monitor that they actually work. The microcontroller has a multi-channel 12-bit analog to digital converter. This is not extremely accurate compared to the 24-bit ADCS used for the sensor signals, but far sufficient to perform sanity checks on the voltages, and comes for free with the chosen microcontroller. The 3 MEMS gyros in the system are resonating structures driven at the respective resonance frequencies. The measured resonance frequencies can be read from the controlling ASICs and monitored by the self-diagnostic function. This effectively gives a continuous self-test covering the complete proof mass of the gyros. As the system clock is used as time reference to these measurements, the monitoring of resonance frequencies will also cover system clock itself. Temperature is a good indicator of the health condition of any system, including us humans. In our STIMs, there are one temperature available for each sensor signal sampled and used for temperature compensation. In addition, there are another 4 temperatures available in the system. By making all the temperatures available to the self-diagnostic function, they can be individually checked to be within expected temperature range. The diagnostic function has been further enhanced to also look at the difference between individual temperatures. All in all, more than 100 parameters are monitored between 50 and 2,000 times a second, depending on parameter. There is even a test to check that the diagnostic function itself is running, reported in bit 85 of the self-diagnostic register. Each data package transmitted will include a status byte per sensor cluster. This is a condensed version of the relevant monitored parameters related to the given sensor cluster. Status of each of the more than 100 tests are available upon request by the user. The processing of the sensor signals will be unaffected by the result of the self-diagnostic function. The STIM will process and output data continuously. It is up to the user or application to use the information in the status bytes to handle any given error condition. And this completes the first half of my presentation. Back to you, Alan.
Thanks very much for that deep dive into IMU design. We're going to pause for a little bit and give the audience a chance to chime in with some questions. I'll have a question for you in a moment, Reidar, but first I want to reach back to Ralph's presentation because we had a couple of questions there. First one, Ralph, why is it difficult to achieve high performance in a miniature gyroscope?
Yeah, thanks, Alan. If you have a mechanical transducer element or a spinning wheel, the sensitivity of the transducer element to rate decreases, goes with mass times length squared. And this is in contrast to accelerometers where the sensitivity scales just as mass times length. So as you shrink your gyro transducer element, you start to lose sensitivity at a faster clip than you do in the accelerometer case. So that's why miniature gyros are a particular challenge.
Thanks, Ralph. You know, I have to confess to some technology-ism on my own part. After 20 years editing GNSS magazines, I thought that, well, GNSS is really pretty highfalutin science. And, oh, inertial, well, that's fairly simple stuff. Well, you know, that can be added on. But I'm learning during the course of this webinar that inertial technology is incredibly complex and fully so the equal of satellite technology. Another question for you, Ralph. Could you elaborate on the challenges of developing a resonating optical fiber gyro?
A lot of it comes down to the optical source itself. With a conventional IFOG, the optical source lies outside the optical sensing pathway. So the wavelength spectrum of the source is intentionally broadened to prevent the formation of local interferometers, local etalons in the optical pathway. So you have a short coherence length, so the only interferometer that forms in an IFOG is in the coil, which is where you want it. With a resonating case, that's going to require a narrow line width laser to probe the optical resonance of the ring. So that introduces some potential sensitivities to backscatter effects. So what you see some people doing is using different modulation schemes to probe the clockwise and counterclockwise resonances separately, to make sure the backscatter effects occur at frequencies that are outside the band of the rotation response. So there's a lot of sort of optical processing jiu-jitsu that's being used to make that architecture work.
Thanks again. Reidar, a question for you. Data integrity, of course, is critical in almost any application, and the more demanding it gets, the more critical the integrity becomes. How do you ensure that the received data is correct and not corrupted in the signal path from the sensor to the user of that data?
Well, in addition to sending information about the health condition of the product, we have also had focus on the transmission of the data itself. First of all, we chose to use an RS422 interface, which is a very robust interface. And as our product may in some cases be placed far away from the receiver, the RS422 interface can surely handle that. Secondly, there are several features in the data packages that can help the receiver to validate the integrity of the transmission. Most important being CRC32 checksum. Next, a counter has been included that would really reveal if one or several data packages have been lost. We have also added some features to support synchronization to the data packages, and also offer integration of the signals, which could reduce the severity of a lost data package.
Thank you. And may I say I was simply staggered by the number of parameters monitored and the frequency at which they are monitored, all in that little device. It's doing its job and also looking at itself doing its job. I wish I had that capability. Lori, let's go ahead with our next poll.
Okay, happy to do that. On the screen, we have our next poll question. And we'd like to hear, what level of gyroscope bias instability performance does your application require? So it looks like we do have a front runner there, but Alan, what are your thoughts?
Well, we have what's known in science as a bell curve here. Obviously, the sweet spot is right in the middle. Most of our audience has a 0.01 degree per hour requirement, and then lesser on either side. I want to relate it to a question that has come in from the audience. I want to look at this when I ask Ralph a question about the different grades of gyroscope. Let's return. We're going to resume with Reidar, and please give us the second part of reliability by design.
Thank you, Alan. With a large diversity in applications and customer needs, Sensonor has established its own standard qualification programs. These come essentially from MIL Standard 810, with some exceptions. Feedback from customers so far tell us that programs fulfill most needs, and the results give our customers valid data in assessing lifetime behavior. Sensonor is always open to discuss special characterization or qualification needs. The one-year stability program is run in series on typically 8 IMUs and takes less than 3 months to complete. Between each step, a full characterization over temperature and measurement range is performed. This gives us additional information about the product's response to each specific environmental load. The 10-year qualification program is run in a parallel fashion. It involves in the order of 70 IMUs and takes typically 5 months to complete. Parts are fully characterized before and after each environmental load. For power tests, like high temperature operating life, the output from the IMUs are recording during the complete 1,000 hours. Sensonor will later this year introduce products in a hermetic package. The 10-year qualification program is already completed. We have now started to run the program again on the same parts, which will give us the performance data over an equivalent lifetime of 20 years. Hermetic parts will be available late 2020. Here is a summary of the recorded gyro and accelerometer bias drift during the 1,000 hours of high temperature operating life. Looking at the relative drift of gyro bias in the left-hand plot, one can see a considerable improvement in the STIM gyros from 2015 and today, comparing blue and red lines. This is the result of continuous improvement programs and better understanding of drift mechanisms. The drift for the gyros in a hermetic package is even better, as expected. The plot to the right verifies that the improved accelerometers in the new STIM 318 also show improved performance in HTOL. Most applications for tactical grade IMUs involve vibrations. Several design features reflect our focus on robustness towards vibrations. For instance, the internal design requires several PCBs to hold sensors in different orientations. No connectors are used. All PCBs are interconnected by the use of flex being an integral part of the PCB. There is only one connector, and that's the micro D connector used for connection to the application. Here, threaded holes with helicoils are provided to enable a secure mounting of the plug. During the internal design of the IMU, finite element modeling was performed and fixation points of the PCB identified to ensure that resonance frequencies are high and away from the resonances of the gyros. The MEMS design is simple, and our technology does not involve complex finger structures to operate. The butterfly design of the MEMS gyro is balanced to give high mechanical common mode rejection. As the vibration sensitivity of the MEMS gyros is much lower in two directions, the gyros have been oriented in such a way that all three gyros have low sensitivity to vibration in the X direction of the IMU. This feature can be utilized if the application has most of its vibrations in one particular direction. The vibration performance is verified through extensive testing of the final system. 20G sinusoidal vibration is a part of our one-year stability program, and the 14.8 GRMS high-performance aircraft random vibration test is part of our standard 10-year qualification program. Earlier this year, the MEMS gyro was tested at 20,000 G, and results indicate that the gyro is a potential candidate for a gun-hardened IMU. Despite the fact that Sensonor's product has not designed specifically for space applications, they have found increasing popularity in space, and several hundred STIM products are currently orbiting the Earth in satellites or used in launch rockets or other missions, based on the simple fact that they work. In order to support customers in this segment and to gain know-how of our products, Sensonor performed on its own initiative proton testing and total ion dose testing in 2018 on STIM 210 gyro modules and STIM 300 IMUs. A total number of 40 parts went through the characterization. The obtained data will help our customers in assessing the effect of radiation and the need for shielding. This slide shows an extract of the test results, this being from the TID tests. The plots to the left show that all parts passed 5K rad for powered parts and 7K rads for unpowered parts. The upper right plot shows that gyro bias is unaffected by any of the applied doses for all the parts that survived the test. The lower right plot shows that accelerometer bias is affected by increasing dose when the part is powered, but not when it's unpowered. This work was partly funded by the Norwegian Space Agency and presented at the SmallSat conference in Utah in August 2019. The complete report can be obtained upon request. All parts failing the radiation tests have been subject to failure analysis. The analysis revealed 3 components that seem to be less robust towards radiation. Based on this, Sensonor has designed a prototype IMU, currently under characterization, where all the identified components have been replaced. New radiation testing is scheduled towards the end of 2020. Finally, some words about ongoing activities. A new IMU is on its way based on STIM 318. This will be named STIM 320 and have improved gyro noise performance with an angular random walk of 0.1 degree per root hour. In addition, the product will offer a pulse per second input. Expected availability is in Q4 2020. Sensonor will this year introduce products with hermetic packaging. First products out will be the STIM 277H with a form, fit and function as STIM 210 and the STIM 377H with a form, fit and function as STIM 300. In addition to being hermetic, these products will have some space adaptations, as they will be cleaned and packaged in a dust-free environment and will not be painted. Both products will be available late 2020. Finally, as mentioned, we are currently making a modified version of the STIM 300, where parts failing the radiation test performed in 2018 have been replaced. Radiation testing will be completed in Q1 2021. And that completes my presentation. Thank you all for listening, and back to you, Alan.
Thank you, Reidar. We're going to go now into the frontiers of space with LeoStella. And first, we're going to hear briefly from Brian Reidar at LeoStella, and following that, the technical portion of the presentation from Ryan Robinson. Ryan is the lead GNC engineer at Guidance, Navigation, and Control, that is, engineer at LeoStella. He's responsible for the design, development, test, and delivery of ADCS subsystems on LeoStella satellites. He received his bachelor's, master's, and PhD in aerospace engineering from the University of Maryland, College Park. Technical areas of interest include attitude determination and control systems design, sensing and actuation, nonlinear dynamics, and autonomy. Before we hear from Ryan, let's have a couple of words from Brian.
All right, thank you. Just a quick intro on the topic. So at LeoStella, we build satellite constellations, and we wanted to talk about the application of some of these technologies to that market. Really what we do is we focus on the commercial industry of satellite-derived products and services, economic forecasting, humanitarian response, data security, and others. Now, as you might expect, that industry is really only possible when the commercial business case closes, which is a different perspective on compared with traditional space missions. That drives a lot of pressure on satellite cost, while also requiring very high performance systems that can meet those products and services. So at LeoStella, we spend a lot of time and effort developing the right balance between performance, risk, and cost. And one way that we do that is to leverage tactical grade components, especially ones that can survive the launch loads, radiation exposure in an on-orbit thermal environment, while also maintaining off-the-shelf costs and schedules associated with that. A good example, actually, is the Sensonor IMUs. We use them extensively in our product line. They're ruggedized components. They work very well with our satellites. And as a satellite manufacturer in the new space market, we're really always looking for industry partners that lean forward and extend tactical components to the new space applications, which is really just exploding right now. There's a lot of opportunity there. Let's go to the next slide. You might wonder, how is this used? And happy to talk about that later if there are questions. But I thought I would put a splash screen up here with a couple of recent use cases. I won't go into details on these, but you might want to look them up if you're interested in some of the recent news on leveraging these kinds of satellites. But at this time, I'll hand over the microphone to Dr. Ryan Robinson, obviously, per the introduction, the architect of our attitude determination control system. Ryan will tell you all about our satellites, the use of IMUs, and you'll get to see some actual real data from our on-orbit satellites too. Ryan, over to you.
All right, thanks, Brian. Let's dive deeper into how we use inertial navigation systems in our Earth observation satellite designs. LeoStella designs and manufactures satellites like the example pictured here on the right for proliferated constellation-level remote sensing. This constellation-level manufacturing requires high-volume production, which we've implemented in our state-of-the-art facility in Tukwila, Washington, to optimize efficiency and minimize cost. Each satellite is comprised of many systems working together. The system I'm going to be highlighting today is the Attitude Determination and Control System, or ADCS, which is responsible for maneuvering, pointing, and stabilization. Earth observation in particular demands high agility to maximize the number of images taken per orbit, but also high precision to maximize the quality of those images. The ADCS works in concert with the other systems here, propulsion, power, comms, payloads, and structures, to meet these performance requirements in the unique space environment. The ADCS also performs other critical functions such as detumbling after launch, tracking the sun to keep the satellite power positive, and pointing communications antennas at ground stations. The driving requirements for Earth observation satellites in low Earth orbit include high precision in position, attitude meaning the orientation of the satellite, and rate, the body rates of the satellite. To maintain pointing on a target, the satellite, which is operating at 7 kilometers per second, needs to rotate over the target at a relatively high rate while maintaining good pointing. On the right is an exaggerated illustration of the contributors to overall geolocation error of the images that are taken. The satellite's position error, which is based on the accuracy of the GPS receiver, translates directly to position error on the ground. And then attitude error, which is the difference between the desired and the actual orientation of the satellite, contributes additional error. Besides good pointing, image quality is also hugely important. This depends on minimizing smear, which is the relative motion between the telescope bore sight and the target when the image is taken. Ideally, the satellite should have significantly less than 1 pixel of smear on the telescope's camera sensor. In general, we're interested in finding cost-optimized component solutions, as we'll be using these in constellation-level high-volume production. But reliability in the harsh space environment is also critical. This includes thermal variation, vibration and shock, vacuum, and radiation effects. Let's take a closer look at the ADCS architecture. So you'll see on the right a representative design with a variety of sensors and actuators, including Sensonor IMUs, which we've been very pleased with. These components are combined in a feedback loop of sensing, estimation, and control, and actuation to achieve the precise pointing required. The star trackers and rate gyros, I'll point them out here, star trackers, and then the rate gyros are within the IMUs. They're critical for fine pointing. They work in a complementary manner, with the star trackers providing attitude and orientation measurements at low frequency, and the rate gyros providing body rate data at high frequency. Inside the ADCS software, we use a Kalman filter to blend both of these types of measurements with a model of the system dynamics to estimate the attitude at the same high frequency as the rate gyros. Additionally, the Kalman filter can estimate and correct for gyro bias in real time. To maximize accuracy and performance, it's important to perform calibration on the star tracker gyro combination to correct for possible misalignments. In a later slide, I'll show how calibration improves attitude error. So, the driving requirements of the IMU itself are low gyro noise and angle random walk, low bias drift. On the right here, you'll see a chart of real on-orbit data that shows the Kalman filter's estimated gyro bias for a month in orbit. And this is well within what we expect and require. And the Kalman filter is easily able to correct for this bias. We also want high measurement rate. And of course, we want all of this in a size, weight, and power efficient package. So this slide shows sample results from 2 target tracking simulations that are identical except for the one on the right having double the amount of gyro noise. So on the left we see the high accuracy gyro simulation results. The top plot tracks the spacecraft's state, so whether it's slewing or tracking and whether it currently meets pointing and rate requirements. The middle plot shows a few different attitude error metrics, the most important being the black line. Let me try to point to it here. And the green diamonds on that black line represent points in time where a star tracker measurement is available. So that's total attitude error. And then the total attitude error you can see on this plot remains low throughout the tracking portion as the body rates between the star tracker measurements are propagated smoothly. The rate error down here is at the bottom. It is basically the same as the attitude error plot, except that here we see rate error. And you can see that that also stays below the threshold for image constraints to be met. Turning our attention over here to the higher gyro noise simulation, the increased noise is directly visible in the bottom plot here, the red and blue lines, which are estimation and control rate error. Note that the total rate error, which is the black line, only increases slightly because the bandwidth of the system is significantly lower than the frequency of the noise. The greatest effect we actually see here is in attitude error, failing to meet image constraints over a significant portion of the tracking. This is because the noisy gyro measurements force the Kalman filter to maintain greater uncertainty when propagating the attitude estimate. And like I said, because of the high attitude error, an image capture might have been at least partially off target. So in this slide, I want to use on-orbit data to illustrate the effects of calibration. The plot on the left shows control error, both attitude and rate control error, before calibration, where during tracking we see significant jumps in the attitude control error when a new star tracker measurement, that's circles. So you can see here a big jump here when we get a new star tracker measurement. When those are taken, it indicates that the body rate propagation between star tracker measurements was inaccurate, and that without star tracker measurements, the attitude estimate would have quickly diverged from the true attitude. Usually this is because the IMU axes are slightly misaligned with respect to the star tracker. The star trackers themselves are calibrated to the telescope separately. The plot on the right shows control error from a tracking event after calibration, where the misalignments have been corrected, so body rate error, maybe you can see my mouse, I'm not sure, is accurately being estimated. Note that the tracking is much smoother, there are no jumps, and the attitude control error is maintained at the low levels we desire. So the last slide here, this is just kind of a wish list of future technology developments in the inertial sensing space. So we'd of course love to see continued improvements in performance, robustness, size, weight, and power, and cost efficiency. One interesting part of our application is that most MEMS gyros are sensitive to helium, and helium could be present and unaccounted for on, for instance, the next wave of small launch vehicles we're interested in launching on. So for fully hermetic IMUs that are also low cost would significantly mitigate that risk. Radiation tolerance is always a concern, and any hardware and software improvements to increase robustness to radiation will reduce risk on our platforms. And finally, with the move to more efficient propulsion methods, such as Hall effect thrusters, it would be useful to have these very sensitive accelerometers to verify thrust performance. We're talking tens of micro Gs in that case. But overall, we see a very bright future for our products because of the continued innovation of the inertial sensing industry. That concludes my part of the presentation. Thanks for listening. Back to you, Alan.
Thanks very much, Ryan. We have some questions for you, and for the rest of the panel, but first we have some questions for the audience, and we actually have 2 questions, so get your mouse clickers ready. The first one relates to something that you brought up, Ryan, in your last slide, fully hermetic IMUs. This would be physically sealed enclosures that are important for storage over time and for reliability over time, long-term stability. Audience, we'd like you to answer this question. How critical is the need for fully hermetic IMUs in your solutions?
All right. Any thoughts on these responses, Alan?
Well, clearly a trend is developing already. Nearly a fifth of our audience is there with requiring a fully hermetic enclosure. A quarter is getting there. Well, I should say half is getting there. It's either important but not yet critical, but becoming increasingly important. So Sensonor and any other inertial manufacturers in the audience, take note. This is a coming thing. We're going to have one more question for our audience. Lori, here we go.
All right. Yeah. Which is the leading requirement for inertial in your application? And options there: low gyro noise, angle random walk or ARW, low bias drift, high measurement rate, or minimized size, weight, and power. Any thoughts here, Alan?
Well, it's a pretty hard question when you ask someone of your many requirements, which is the leading one. Sometimes it's hard to choose, but clearly 63% of the audience has been able to make a choice, and it's not surprising that low bias drift is the leading candidate. I'm sure all those people would have said low gyro noise is also as important, but if you force me to choose, I'll go there. Size, weight, and power, of course, always a consideration. Well, now that we have the audience input, let's get more input from our panelists with questions. Going back to that poll that we just had about hermetic enclosures at Reidar, with respect to the planned hermetic gyro units that you discussed, how do you verify that it actually is hermetic in your production process?
Just first to tell everybody about how we make it hermetic. This is done by replacing the plug, which is or by a glass metal feed through, and then the lid will be laser welded. All the parts will undergo a leak test or a hermeticity test according to MIL standard 883 method 1014 class H, which is, I think, what one would say is helium leak tight. This will be done by using an optical leak tester.
Okay, and one further one for you, Reidar, since we have you at the microphone. In spacecraft designs, power management and power supply capacity is a critical design parameter. Can you comment on inrush current, or have you characterized this in your systems?
Yes, you are right. We have become very conscious about inrush current, especially related to questions and feedback from our customers in space. For STIM 300, as an example, we have characterized the inrush current over temperature and input voltage and found it to be in the range of 1.3 amps. On the new STIM 377H, this is more than halved to around 0.6 amps. And this reduced inrush current design has already been implemented on the STIM 318 and will also be implemented on new products to come.
All right, thank you. Ralph, a question for you, kind of a defining question. Well, it is a definition question. Is there a broadly accepted definition for the various gyroscope and accelerometer grades? You alluded in your talk and your Venn diagram to the different grades. How are they distinguished from one from another?
Yeah, I'd say that there's a pretty well accepted standard for those grades. On the gyroscope side, 0.1 degrees an hour is your navigation grade gyroscope, and that's really derived from a nav grade system. They talk about you want a nautical mile an hour system, meaning if you fly around for an hour, you know your position within a nautical mile. So a nautical mile is equal to the arc length of an arc minute of arc on a great circle on the globe. And that's about 1.16 regular miles. So if you want to know your position to a nautical mile in an hour, then you need gyro rate stability on the order of an arc minute per hour, which is about 0.16 degrees an hour. So that's where your nav grade definition comes from. The tactical grade gyros are on the order of 1 degree an hour, and then the strategic grade stuff is about 10 times or so better than the nav grade. So on the gyro side, that's sort of where your line of demarcation is drawn between strategic, nav, and tactical. On the accelerometer side, 1 micro G is sort of strategic grade, 10 to 50 is nav grade, and milli-G and coarser is tactical grade.
Thanks, Ralph. Ryan, a few questions for you about your application in space. With better star trackers, is a rate gyro necessary?
Thanks for the question. Yeah, you could imagine star trackers with super high measurement rates and super high accuracy, but even then you'd have to kind of differentiate the attitude estimates and might end up with choppy rate estimates. And I'm sure these theoretical star trackers would be extremely expensive. Plus, when star trackers are blinded, either by the sun or earth, you can't use them, and they'll need to reacquire signal afterwards. Most commercial star trackers can't operate above a certain rate. For instance, 3 degrees per second is what I've seen. So personally, I wouldn't build an Earth observation satellite with without rate sensors, especially for an Earth observation satellite. Yeah. So yes, it is necessary, in my opinion.
It's necessary. Next, another one for you. What happens if an IMU is failing? What steps have you taken in your satellite design to ensure redundancy and mission success?
Our flight software in ADCS has multiple levels of failure detection and fallback behaviors. So if an IMU is failing, we can detect either the anomalous data or lack of communication and reset the hardware. We usually have a cold spare, so we could switch to that cold spare. And we even have an IMU-less recovery mode that we could fall back to. So a little more information about that could be we can roughly estimate the body rates using a combination of other sensors, kind of like what I was talking about, differentiating the star tracker solutions. You can do that with other sensors, and that would preserve the mission, but would have significantly degraded performance.
And finally, Ryan, with space becoming more contested, can your satellites operate in GPS-denied environments?
Yes, they can. Our satellites can still operate and perform the mission. Of course, we're going to lose some geolocation accuracy, but LeoStella and our customers do have contingencies for GPS loss. We can use CSPOC TLEs, propagate those, and uplink that kind of ephemeris table to the satellite. Our customers have also used, have been working with other companies that use, I think, Reidar to provide better ephemeris estimates than CSPOC. compared to other applications, the orbital dynamics are fairly predictable. So between kind of ephemeris entries in your table, our ADCS can propagate that orbit and give us a pretty good idea of what our position is.
Thanks. Going back to Reidar, a question for you just about the construction or design. How does an inclinometer differ from the accelerometer in an inertial measurement unit?
Thank you. Well, that is a good question and probably a little bit confusing. The so-called inclinometers in our products are really accelerometers as well, and we provide, let's say, an acceleration output and not, let's say, an angle. They are of a different technology, a thermal-based technology compared to the accelerometers, which is more like a conventional mass spring system. They have a much lower bandwidth, and they were kind of put in from the start as they might provide some advantages compared to the accelerometers. In the STIM 300, we have found the bias long-term stability to be better on the inclinometers, and so one could, let's say, use this feature to improve the accelerometer performance. When we come to the STIM 318, the performance of the accelerometers outtakes the inclinometers, and so when we look at the STIM 320, the inclinometers are no longer there.
Okay. Another question for you, Reidar, from somebody obviously who seems to know you pretty well, wants to know about radiation-hardened IMUs. Does Sensonor intend to work on a radiation-hardened IMU, or perhaps are you already at work? This person read, perhaps attended, but at least read your paper, COTS for Space Radiation Characterization of Gyro and IMUs for LEO Operations, presented at the 2019 SmallSat conference. And perhaps at that time there were some challenges with radiation, but how has this affected your design and product lineup?
Yeah, well, I'm not a politician, so I can give a short answer, and that would be no. Sensonor is not working on radiation-hardened IMUs. Our focus is to make a standard portfolio that can reach as many, let's say, users as possible. However, always open to make special adaptations for special requirements, but the volumes, let's say, in this radiation-hardened IMU field is really too low for us. So, and it would be too specialized. As I said, we are doing measures to make our products more robust, but we have not, for the new design either, chosen rad-hardened components as such. So we are making improvements within, let's say, the boundary of our products as they are.
Well, thank you for that frank response. It's refreshing in these times to get an answer that is not politically driven. Let's turn to Brian. Brian, I'm curious, this whole LEO thing, why use a constellation of Earth imaging satellites instead of just a few large ones with higher performance?
Yeah, that's a great question. I think there's clearly a trade-off there between a few exquisite satellites compared with a large constellation of small sats. And the reason to do that is really about the insights and the temporal information that can be gained with a constellation of many satellites in a low Earth orbit. There are many examples, but I'll give you just one. For instance, if you were to compare a high-resolution optical satellite that might take a picture of, call it the Port of Seattle, once a day, and it can count the number of boats and say, hey, at 10:30 in the morning every day, there are X number of boats in the shipping lanes in the Port of Seattle. That's great information, has very high spatial resolution, but very low temporal resolution. You only get it once a day or maybe twice a day if you've got a couple of satellites. If you instead take that same amount of money that you would have spent developing, building, and launching that one exquisite satellite or the few exquisite satellites, and you use that with several dozen smaller, cheaper satellites into maybe slightly different orbits, but still low Earth, then you can use that constellation as a broad capability. And in this case, you could image the Port of Seattle every hour or every 15 minutes. Now, let's say you do this and you extend this constellation. You're not just looking at the Port of Seattle, but maybe you're looking at every single shipping port in the world. Then all of a sudden, you can put all that data together real time and have a real-time tracking and monitoring of global shipping activity, which is interesting. But where it becomes valuable is when you turn that into economic projections or other insights and analytics that can be derived from that. That information, especially real-time, temporally high temporal resolution information about patterns of life in the world, really cross-cut into a number of different industries. And that's, why have we not done that in the past? Well, in the past, sort of the more traditional space, launch was so expensive and satellites were so expensive that it just didn't make sense to create a business model that can do that can exploit that capability. But that has changed. Satellite components, satellite manufacturing, and much more affordable launch opportunities and launch costs really enabled these business cases to be created that exploit that.
Thanks, Brian. It's fascinating to see what's going on in the world of LEO satellites and these large constellations of small satellites. Some of them I've read as small as a bread box. They're up there returning highly precise data to Earth. A couple more questions for Reidar, and then we're going to close it out. You talked about low volume in one sector, Reidar. What about the automotive sector? For one attendee wants to know, for automotive sensor high temp tests, did he see correctly that in your tactical grade sensor, the upper temperature testing goes up to 85 Celsius? And do you have products that go to 125?
Okay. It is correct that our STIMs today are specified at an operational temperature of 85 degrees and storage temperature at 90 degrees. Most of the parts, internal parts or components, are either specified to from minus 40 to 105 or minus 55 to 125. This is again the design philosophy to have as much margins as possible in the products. To meet a 125 degree application, I would say is not really an impossible thing. I think we would need to do again an evaluation of internal components, and maybe some of them needs to be upgraded. But from what we have done so far on highly accelerated live testing in our halt chamber. The products function up to, I would say, 140, 150 degrees today, not then having done any performance check at that level, but I think 125 degrees would be, let's say, a possible spec to meet if such opportunity should arise.
Interesting, and clearly plenty of room for discussion between Sensonor and customers. We're going to close out with one final question for Reidar, but first I'd like to encourage the audience to, after we've signed off, to complete the post-webinar survey. And our final question, Reidar, can Sensonor discuss what you changed to improve the gyro and angle random walk for the products coming out later this year? How did you accomplish this?
Yeah, well, that's another good question. So it means we have a very good audience today. The improvement of angular random walk from 0.15 to 0.1 degree per root hour is accomplished by a combination of increasing the excitation amplitude, because the noise will be directly proportional to, or to 1 over the change of excitation amplitude, and the other thing is to perform some special sorting of MEMS dies, as we measure a lot of performance parameters all the way at the MEMS level. We can then do some special sorting, and we can do a small, let's say, increase in the excitation amplitude, which then will give us a better performance. We have been, say, very careful about adjusting the excitation amplitude, and that the reason for that is that this gyro was, say, proven its reliability through the 2 million parts we produced in the automotive. So we have, let's say, a very good reliability track record there, with more or less no, let's say, failures. So we have been, say, very reluctant to change the excitation amplitude or increase it, as it could be a compromise to reliability. We have now conducted several reliability tests to verify that this slight increase in excitation amplitude will not affect the reliability, and so that is how we accomplish the 0.1 degree per square root hour.
Thank you. Well, that about wraps it up. We've spent a perfectly good hour and a half learning more about inertial technology, its finer points, and its applications at the frontiers of space. I'm going to ask the audience for their, ask the panelists for their just a couple of concluding comments. We'll go in order of presentation: Ralph, Reidar, and then Brian and or Ryan, and then we'll close it out. Ralph, final word from you.
Thank you, Alan. Hope everyone enjoyed our talks today. I know I enjoyed listening to everybody else. I thought that some of the questions were very interesting in terms of what does the inclinometer do? Can we get away without a gyro and just use a stellar sighting? And I think what you're going to find is you're not really going to be getting rid of anything. You're going to be using all of those systems together to give you a very robust PNT solution, no matter what your application is. Just GPS and inertial The line is really blurred now between what's the inertial solution, what's the GPS solution. There really isn't a line of demarcation there with all these deep integration technologies that people are using now. So I think you're going to have all your subsystems working together to get you one answer. And it's an interesting way of looking at things, especially someone like me who's really just been a sensor guy my whole career.
Thanks, Ralph. Reidar?
Well, I hope all the attendees now can say that they have heard about Sensonor, and that I've got an impression of a company that takes reliability seriously and deliver robust products that can be trusted. And I thank you all for very good questions. Yeah, I'm very pleased.
Wonderful. We're all very pleased with you. Brian and Ryan, final words.
Yeah, just a big thank you for all that attended and co-speakers and the panel. I think this is a great discussion. We are really trying to disrupt the satellite market, and we can't do that without really strong partners that are leaning forward and taking awesome technology and making it available for space. So having this discussion and seeing the way the industry is going, I think that's extremely helpful in that sense. There's a lot more to come. Space is going to become, very, very big. And I think those that are leaning forward are going to be a big part of that. So I just want to thank all of you who are working in the industry in doing that. That really helps us with our mission. Ryan, thoughts?
Yeah. And I just want to echo what Brian said. Thank you to the panel speakers and attendees. I enjoyed it very much. I learned a lot of new information from our other speakers and in the Q&A. For those not in the space industry, I hope we gave you an interesting new perspective. LeoStella is going to continue to integrate the best parts from the industry into our components, and we look forward to the future.
Thanks very much, gentlemen. A warm round of applause for our panel. Thank you so much to Sensonor, our sponsor, for making this webinar possible. And thank you to all of you out in the audience for attending. I want to remind you again that there is a post-webinar survey. It's very valuable for us in preparing future webinars, as well as to Sensonor in gathering information. Lori will tell you in a minute how you can recapture the content of this webinar and share it with your colleagues who may be interested. And I'll tell you finally that this webinar will be, in brief, encapsulated in a future issue of either Inside GNSS magazine or Inside Unmanned Systems. And with that, a final thank you to everyone around the world who attended. Back to you, Lori.
Thank you, Alan. And again, just echoing, thanks for joining us. This is Lori Dearman saying, hope we see you on the next one. Bye for now.